Light steel framing has gained a high market share internationally. A full-scale shaking table test was commissioned by the National Association of Steel Framed Housing New Zealand to investigate the seismic performance of light steel framing with brick veneer exterior cladding. This was undertaken at the University of Melbourne, Australia.
NASH in New Zealand, it's the National Association of Steel Frame Housing. NASH promotes the industry as a whole. Most of our members are all the people who are producing steel framing in New Zealand, and our aim is to move the industry ahead.
We're doing a representative test on brick veneer on steel framing under earthquake loadings, where we are wanting to determine as realistically as possible the expected performance of brick veneer on steel framing under different defined levels of earthquake loading. We are hoping and expecting that for the different levels of earthquake loading we will have no damage or minimal to no damage under what's called a serviceability earthquake. We are hoping on the basis of the performance we've had so far that in fact the brick veneer will remain largely intact.
The test house was developed to model the behaviour of a real house under seismic loading. It was 2.6 by 2.8 metres in plan and 2.4 metres high. To simulate the critical case of long brick veneer walls to a house, the front and side walls were separated at the corners. The exterior brick veneer cladding was constructed using standard 70 series bricks. The brick veneer was attached to the steel frame with Type B brick ties in accordance with normal industry practice. The ties were fixed to the flanges of the steel studs using a single screw that was fastened through the thermal break. The test house had, in one direction, 2 brick veneer walls without openings. In the other direction, one wall had an opening for a window and the other had an opening for a door. To monitor the forces being transferred between the exterior brick veneer and the light steel framing, strain gauges were fixed to the wall ties. To monitor whether there was any evidence of tie pull-out from the mortar during the tests, video cameras were mounted at the top of the cavities. The interior finish to the test house was comprised of 10mm thick standard plasterboard. The 90mm wall studs were spaced at 600mm centres. A 1500 kilogram roof slab was added to model a typical house roof. The test house, with a natural frequency of approximately 6 Hz, exhibited the same dynamic characteristics as those of a typical full-size brick veneer house. The test house was subjected to various levels of the 1940 El Centro north-south earthquake strong motion record. This Californian earthquake has become the international benchmark for earthquake testing and engineering and is recognised by the New Zealand Earthquake Standard. Test 1 and 3 subjected the test house to 0.89 times El Centro. This represents a strong earthquake of approximately 6.2 on the Richter scale. No sign of any damage from these tests were observed. This level of loading is greater than ultimate limit state levels for Auckland and Hamilton and is approximately equal to the ultimate limit state level for Dunedin. It also represents the serviceability limit state for high earthquake regions in New Zealand. In Test 2, the walls without openings were subjected to ultimate limit state out-of-plane loading. After this test, only small hairline cracks were observed in the plasterboard lining at window top corners and some very limited hairline cracks at locations in the brick veneer adjacent to the window opening.
Well, the ties and the insulation suffered no effects at all. The studs seemed to move about 2mm or so. Brick veneer just moved as a solid unit, no sign of any local deformation or cracking, and no sign of any damage whatsoever.
In Test 4, the excitation was applied to subject the walls without openings to maximum considered earthquake, MCE, loading in the out-of-plane direction. This MCE loading was equivalent to 1.72 times El Centro, which represents an earthquake of 8.4 on the Richter scale. MCE is defined as the maximum considered earthquake representing a very rare event with a return period of 2,500 years, compared to the ultimate state limit earthquake that has a return period of 500 years. This level of loading required to be met for the steel framing and brick tie system to satisfy code requirements in New Zealand. After this test, a minor increase in cracking to the plasterboard at window corners was observed. However, there was no visible damage to any of the ties. Test 5 consisted of subjecting the test house to an MCE level of load in the other direction, which resulted in the walls with the door and the window being subject to out-of-plane loading. The test house passed all the requirements for MCE and everyone involved was delighted with the excellent performance. The decision was then made to increase the loading to determine how much reserve strength remained in the test house. In Test 6, the load direction was changed again to load the walls without openings in the out-of-plane direction. In this test, the loading was 1.16 times MCE level, which was equivalent to 2 times El Centro. As can be seen, there was no noticeable rocking of the brick piers at the base of the window. After this test, hairline cracks that extended across the pier base were observed. However, there was no visible damage to any of the ties or the steel frame. In Test 7, the level of loading was increased to 1.34 times the MCE level, which was equivalent to 2.3 times El Centro. As can be seen, there was an increased rocking and cracking of the brick piers at the base of the window during the test. From a visual inspection of the test house, there was no evidence of pull-out of any of the ties or damage to the steel frame. In Test 8, the level of loading was increased further to 1.51 times the MCE level, which is equivalent to 2.6 times El Centro and equivalent to a magnitude 9 on the Richter scale. As can be seen, there was further increase in rocking and cracking, which was augmented by partial failure of the connection between the diagonal brace and the top plate to the walls with the openings. Again, there was no sign of tie pull-out from the steel frame or the brick veneer. However, there was evidence of the ties causing a permanent indentation in the thermal brakes.
We've had the pleasure of using our shaking table, the one in the background there, to perform earthquake simulations on the test structure. And as you may have seen already, the test house was subjected to a series of earthquakes ranging in severity from serviceability to well beyond ultimate.
Tell us what the results achieved and how you would interpret them.
Well, we certainly have had very good results out of these tests. The test has performed exceptionally well. At serviceability, it showed no sign of damage whatsoever. Even at ultimate limit state, the house was in very good shape. There was no evidence of damage to the brickwork or any distress to the brick ties. Only at ultimate minor cosmetic damage that would be very easy to deal with. But in terms of ultimate performance, it did not collapse or show major deterioration up to in excess of 2.5, 2.6 El Centro.
What do you think this means to the steel frame industry in New Zealand?
Well, certainly this should give the industry a boost in providing this high quality product for any part of New Zealand with the confidence and assurance this form of construction will perform exceptionally well to the satisfaction of current standards and beyond.
In Test 9, one last attempt was made to fail the test house by increasing the loadings to 1.57 times the MCE level, which was equivalent to 2.7 times El Centro and met the capacity of the shaking table at the University of Melbourne. This was equivalent of a devastating earthquake exceeding 9 on the Richter scale.
Are you pleased with the results?
Extremely pleased. It's performed at the right at the upper end of my expectations. It's as good as I could have hoped for and certainly better than I expected.
What does this mean for the steel frame industry?
it means that we have a system that is incredibly robust in earthquakes, and it means that we can show that our system will deliver the best possible performance in an earthquake, and performance that is, I believe, better than, or demonstrably better than any other system that's been tested in New Zealand to date.